All right, so with chapter 5, we're going to be looking at thermochemistry. And if we think about what the prefix thermo means, it's going to be referring to heat. So thermal, for instance, has the same prefix there. So it's going to be referring to the heat of chemistry, so the heat of reactions. And what we're going to see is certain reactions are going to release heat, while other ones are going to absorb heat. And then when we're talking about heat, we're really talking about just a specific type of energy. So we'll also look at energy just sort of as a whole as well. But later on in the chapter, will be more focused specifically on heat. But when we're looking at energy, we're going to have two different kind of components to it. Energy that can be used for work, as well as energy related to heat. And when we're thinking about work, if you've ever taken a physics course before, often it's defined as force times distance. So the amount of force we apply over a given distance. So if we apply more force, we'll see work goes up, or if we apply it over a longer distance, work's going to go up as well. And then with heat, again, we're thinking about energy. So if we look at the picture here, we've got a Bunsen burner, so you can see the two cones of the flame, and then we've just got a spatula above it, so it's starting to glow, kind of that orangey red, because it's getting heated up. It's getting more of the energy there. And with heat, I just want to point out that heat's always going to flow from warm to cold. So cold itself actually isn't a thing. It's just the absence of heat. But whenever we have heat, it's always going to move from the hotter object to the cooler one. So if you think about it in the wintertime, if you're sitting by a window inside and you open the window, it's going to start to feel cold. But it's not actually the cold from the outside coming into your house. It's going to be the warmth from inside, the warmth from your body even leaving and going out to the colder environment outside. So that's why it's going to feel cold to you, because the heat's actually going to be leaving your body in that case, because it's always going to go from warm to cold. And then with energy in general, we're going to see that there's different types of energy. So if we look at the picture here, on the left-hand side, we've got a cyclist at the top of a hill. And on the left-hand side, we can think of them as motionless. So on the left-hand side, they're going to have just only potential energy if they're not moving at all. But once they start to move, they're going to start to pick up speed. And what we're going to see then is they're going to have kinetic energy, so the energy of motion. And you can see the equation here. Kinetic energy is equal to 1/2 times the mass of whatever that thing's going to be, times the velocity squared. So with it, the unit there, get the draw thing. The unit for that then is going to be, kilogram. And then velocity is going to be in meters per second. But since we're squaring that, we're going to really have meters squared per second squared. And what we're going to see is that's also going to be equal to a joule. So just a capital J there. But once this person starts to roll down the hill, now they're starting to get that kinetic energy. And I should also mention with potential energy, if you've ever taken physics again, you may have seen potential energy is going to be related to the mass times the gravity times the height. So if you think about an apple and a tree, a larger apple is going to have more potential energy when it's just sitting in the tree because it's got more mass. But also if we have that potential energy, or if we have that apple higher up in the tree, it's going to have more potential energy just based on the height of it. And the reason it's going to have more potential energy higher up is because once it starts to fall, similar to the cyclist starting to move down the hill, once it starts to fall, or once the cyclist starts to actually move, now the potential energy it had initially is going to start getting converted to the kinetic energy, because we're going to see with energy, similar to the mass of chemical reactions, we can't create or destroy it. We can only have it transfer from one form to another. So in this case, it'd be potential to kinetic, and the same thing with the apple falling out of the tree. All potential energy while it's in the tree, but once it starts to fall, as it starts to gain more and more speed, the kinetic energy is going to increase because it's converting that potential energy it had into that kinetic energy. And then with this, even since it's not going to be a perfect system, there's going to be friction between the bike and the ground. friction with the air that you're riding through. So you're also going to lose some of that energy through heat. But the total amount of energy is still going to be the same. We're just going to have it get converted to heat rather than kinetic energy. And then, like I said, with the unit there, kilogram meter squared per second squared is just going to be equal to 1 joule. And then with that, what we'll see is that 4.184 joules is also going to be equal to 1 calorie. So with the little c here, and the calorie is based off the amount of heat needed to raise the temperature of water, or 1 gram of water by 1 degree Celsius. And then what I also want to point out here is if you look, calorie with the little c is going to be the energy needed, just like I described, to raise 1 gram of water 1 degree. But the food calorie that you see on like nutrition labels and stuff, that's actually a calorie with a capital C, or a kilocalorie. So that's going to be 1,000 of these calories here. I don't know why they decided on making the unit the same, but just capitalizing it to represent 1,000 of them. But that's just going to be 1,000 of these calories. And then, like I said, we're going to have with energy, only having it change from one form to another or moving, but the total energy can't change at all. So we're going to have, in addition to the conservation of mass, we're also going to have the conservation of energy. And when we're looking at chemical reactions, what we're going to be seeing is that the energy is going to be transferred from the system. So the reaction itself, going to be transferred between the system and the surroundings. In some cases, the energy may go into the system. In other cases, the energy may go into the surroundings. But because those two things are going to encompass the entire universe, we're going to see that the total amount of energy is always going to be constant. And with the system itself, this can sometimes be kind of an odd concept, because in some cases we'll actually see water, even though it may be in the beaker that we're reacting, water itself may not actually be considered the system in some cases. But if we look at the example here, we're taking calcium metal and liquid water, reacting them together to make calcium hydroxide and hydrogen gas. So these 4 substances are going to be considered the system. Everything else is going to be part of the surroundings. So even if we think about these 4 substances, so we put water in a beaker, drop some calcium in there, the beaker itself would be part of the surroundings. The lab bench that we have that beaker on is going to be part of the surroundings. Us observing the reaction is going to be part of the surroundings. And that's why we're often going to be able to feel that energy exchange, because if it's an energy or a reaction that releases heat, it's going to feel warm to us because that energy is going to be going into the surroundings. Or if it's an energy or a reaction that uses absorbs energy, that's going to feel cold to us because now the energy is going from the surroundings into that system. But we just want to make sure that we can always identify kind of what we're considering the system, what we're considering the surroundings, so we can identify that energy transfer between the two. So if we look at this example, in this case we've got some couple different gases. Those different molecules would be considered the system, but then the piston it's in, or the cylinder and the piston above it, those would be considered part of the surroundings, because those aren't actually the reactant molecules or the product molecules themselves. And then, like I said, with these ones, we can have energy transfer between the system and the surroundings. But the total amount of energy is going to be constant. So if we do see a conversion of energy, it's going to be from one type to another, but the total amount is going to be the same. So like with the cyclist here, it's going to be all potential energy to start, and then they'll start to convert some of that potential energy to kinetic. But whatever kinetic energy they gain is going to be equal to the potential energy that they lost. And if we had them get all the way down to the bottom of the hill, assuming that there was no friction, then the kinetic energy they had at the bottom would be equal to the potential energy they had at the top there. But of course, there's going to be friction with the air, friction with the tires on the ground. So we'll always lose a little bit of the heat from that as well. And then this is actually going to be the first law of thermodynamics. So thermodynamics, similar to thermochemistry, where they're interested in the study of heat. But with thermodynamics, it's more of the movement, and it's not specific to just chemical reactions like we're going to see with thermochemistry. Or I guess physical changes we'll actually see as well with thermochemistry in some cases. But just like with the mass, we're not creating or destroying mass in chemical reactions. So when we're looking at the conservation of energy, it's not going to be created or destroyed. It's just going to be transferred from one form to another. It may move from one system to the surroundings, but the total amount of energy within the universe is always going to be constant. So if we look at the reactions here, we can see energy on the y-axis. And in the case of the first reaction, we're starting with higher energy, moving to lower energy. So whatever energy loss is occurring in this system is going to be the same amount of energy gained by the surroundings. So in this case, energy lost to surroundings, meaning that this amount of energy is going to the surroundings. So if we were actually observing this reaction, we may see light being produced. That may be the energy being released. Or a lot of the times, these reactions are going to feel warm to us, just because that energy might be released in the form of heat. And then just the reverse for the right-hand side here. The system is absorbing energy. Again, that energy can't just appear out of nowhere, so that energy is coming from the surroundings in this case. So if we were to observe this reaction, it may feel cold to us because that energy being gained may be gained in the form of heat. And then with the energy, you can see on the axis here, it's labeled as internal energy. We're just going to consider that the sum of all of the energies, basically. So kinetic plus potential energy is going to be accounted for with this internal energy here. And then we'll use the capital E just for energy to symbolize that. And then when we're looking at the change in energy or change in internal energy, just like change in pretty much anything, it's always going to be the final condition minus the initial one. So that's why if we look at the first one here, the system is going to have a negative energy loss because it's going to have a lower final energy. So we'll have a small number minus a bigger one, giving us a negative delta E for the left-hand side here, and then just a reverse for the right-hand side. We've got a larger final energy. So we're going to have a bigger number minus a smaller one. We'll see a net increase there. And then depending on the sign of delta E, so if it's positive or negative, we've got two different terms that we can use to describe these ones. So in the case of this one, delta E is greater than 0, or the change in delta E is greater than 0, meaning that the system is absorbing energy. So in this case, we'd be starting on the bottom, moving up to the top. So we've got a larger final energy than we did the initial. In this case, the system's absorbing that energy, and that's going to be known as an endergonic reaction. And then the way that I remember it is energy is going into the system. And then we've got En, so it kind of sounds like in, because it's going to be absorbed by the system. It's going to go into that system, so we're going to see an increase in the energy. And then we'll see just the opposite. If it's leaving the system, if it's going into the surroundings, now the system's going to have a negative delta E. And in this case, it's going to be an exergonic reaction. And the way I remember that one is just the EX beginning. So it kind of sounds like exit, because energy is exiting the system. And that's why we'd be looking at the left-hand side here. So we're going to start higher up, but that energy is going to leave the system. So we'll finish at a lower spot there. And then just note with these two terms, we're referring to energy overall. So we're referring to that internal energy change. We're going to have very similar terms if we're thinking about the heat exchanged, rather than just the energy overall. But when we're looking at the internal energy, we've got those two different components we can think of. So change in delta E is going to be related to the amount of heat and amount of work done. And it's also going to depend on which direction those are going. So in the case of the picture here, we're having heat and work go into the system. So both of these would be positive values. We're going to see we'll have a positive delta E overall in that case. But in some cases, we'll have the opposite occurring. We'll have those energies, we'll have the heat having the work, leaving the system there. And then depending on exactly what we have, that'll ultimately determine what the sign on that delta E is going to be. So on the left-hand side here, heat's going into the system, work's going into the system. So in this case, the surroundings is going to be doing work on the system itself. So that's why it's going to be a positive W. Whereas on the right-hand side, we're seeing the opposite occur. So heat's leaving the system, negative delta Q. And then with work, what we're going to consider that one is the system is going to be doing work on the surroundings. So typically with work, when we're looking at chemical reactions, we're going to be looking at a change in volume. And if the volume increases, we'll see that's going to be the system doing work under the surroundings. So if we kind of think about a reaction with gases, if we produce more gas, have this vessel increase in volume, we're going to have the system pushing up against the surroundings, so the work's going to be getting done on the surroundings. Where if we have a decrease in volume, we'll see the opposite occur. Then we'd have work going into the system. But like I said, with the heat exchanged, if that's all we're focused on, so we're just focused on Q, so for the heat. If we have heat going into the system, so this would actually feel cold to us because it's the heat's going from the surroundings where we are into the system. This is going to be an endothermic reaction, so we still have that En beginning. So going into the system, we're going to have an endothermic. So now that we're dealing with just heat rather than all energy, we've got thermic in there to specify the heat. And the same thing with exothermic, still kind of sounds like exit, because we're going to have the heat leaving the system. So with these exothermic reactions, we're going to see that those are going to feel warm to us. And then with heat, we've been labeling that as Q so far. We're going to see later on why we sometimes have a different symbol for that. So delta H, we're going to see a lot of the times delta H is going to be the same thing as Q. And with the internal energy, what we're going to see is that's going to be a state function, meaning that it's not going to be important how we get to that condition. It's just going to be sort of important what that condition actually is. And one way you can think about that is in the system below, if we wind up with 50 grams of water at 25 degrees C, the internal energy of this system is going to be the same whether we cool it down from 100 degrees C or we heat it up from solid ice at 0. So what we're going to see is that the internal energy is what's going to be known as a state function, meaning that it's only going to be concerned with what that value is. It's not going to be concerned with how we actually got there. So with it, you can kind of think of distance versus displacement. So if we've got, oops, the pen going again. If we've got some start and some finish, we could take a relatively straight line there between the two. Or we could take some crazy path like that. And when we're thinking about the displacement's going to be the same because we started here, finished here, and that's the case for both of them. So the amount that we've moved in terms of the start and the finish is the exact same. But now when we think about distance, or distance traveled, with the straight line, it's going to be the shortest path. But then the squiggly one is going to be obviously much, much longer. So distance traveled is going to be important in terms of where we actually go. The path we take is going to be important. So distance traveled wouldn't be a state function, but the displacement is going to be. And that's going to be the same thing we look at with the internal energy. It's just going to be concerned with the final, the initial. Doesn't matter how we actually got there. And then if you think about the reason that's going to be is with delta E, we're just looking at the initial minus the final, but it doesn't say anything about how we get from that initial to the final value. It's just going to be those two values themselves, but we could take a straight line path between the two, or we could do some crazy path that goes much longer. But as long as those starting and final points are the same, that's all that's going to matter with these state functions. And what's kind of interesting is even though the internal energy is going to be a state function, heat and work themselves won't be. So if we look at the example here, we've got two different batteries, both going to be fully charged. So if we think about the energy here at the charged battery where it's full, going to have higher energy than when it's a dead battery when it's fully discharged. And in both cases, when we go from fully charged to the dead battery, the delta E is going to be the same. So that's why the energy, the internal energy change, is going to be a state function. Doesn't matter if we short circuit the battery or if we just discharge it by having it run the fan for however long it's going to last. The energy change is going to be the same from charged to dead. But with the short circuit, we're going to lose that energy in the form of heat. Whereas when we're actually running the battery, or running the fan with the battery, I should say, we're going to perform some work with it. We're going to still have a little bit of heat loss, but the heat and the work don't match up. So that's why they're not going to be a state function here, even though the internal energy will be. And for mostly the chapter, we're going to be focused on the heat. So like I said, we'll also be able to see that that's ultimately going to be equal to that capital H. But just to take a look at work for a little bit, like I said, we're going to be focused on changes in volume with work. So if we look at the example here, we've got a cylinder with a piston on it, and then we could have some gases mixed in there. And then a reaction is going to take place that's going to, in this case, produce more gas. So we're going to see an increase in volume. And if we think about what's occurring here initially, there's going to be some force, some pressure pushing down this piston. But then as it expands, as the volume increases, the force on the inside is going to be greater. So the force on the inside is going to be essentially negating and then some. It's going to be overcoming that initial pressure from the outside. So since the system is pushing against the surroundings, when we see an increase in volume, we're going to say the system is doing work on the surroundings. And in that case, we're going to see a negative work value. And with it, we'll be able to use this equation to actually calculate how much work is being done. So with it, we've got work is equal to the negative pressure times the change in volume. So again, if we look at the picture at the bottom here, we've got some vessel with hydrochloric acid at the bottom, and then some zinc just in this little knob. And then we've got a piston at the top. And when we turn that knob, we allow the zinc to drop into the solution. We're going to have a reaction where a single replacement reaction where zinc and hydrogen switch spots. So we're going to have zinc chloride solution and hydrogen gas being produced. So as we increase the amount of hydrogen, we're going to see the pressure increases. So we see that piston moves up higher. We've got a positive delta V here. But like I said, in this case, since the piston's moving higher, the system is pushing against the surroundings. So we're going to have the system doing work on the surroundings. We're going to have a negative W value here. So that's why in the equation, we've just got a negative delta P, or a negative P delta V here. So we just throw in that negative to account for the fact that we're going to have a positive delta V here. If it occurred in the opposite, so if the piston got pushed down, now we'd have a negative delta V, and negative times a negative gives us a positive. So in that case, the surroundings would be doing work on the system itself. And then with this, if you notice delta V, it's going to be because we're assuming constant pressure on the outside. So the atmospheric pressure or whatever, we have this piston sort of equilibrating against initially. That pressure on the outside is going to stay the same. So the work is just going to be directly related to that changed volume. And then with most of our reaction, with most of our processes, we're going to see that the pressure will be constant. So if you think about when we're working in the lab, we're not actually changing the air pressure in that room. So we're going to have constant pressure, and what that's going to allow us to do is use the equation at the bottom here, where H is going to be the enthalpy, which is essentially going to be sort of the heat content of that system. E is still going to be the internal energy, and then P and V are still going to be pressure and volume. So what we can do then is look at the change in enthalpy, look at the change in that heat content. So if we've got delta H, what we're going to see is we'll have delta E plus PV. But since we're going to have a constant pressure, we can then sort of separate this out to have that change in enthalpy is going to be equal to the change in internal energy plus the pressure times change in volume. And then we'll be able to further rearrange this one is based on the equations we just looked at. So P delta V is going to be, or negative P delta V is going to be equal to work. So if we've got positive P delta V, that'll be equal to negative work. And if we think about what delta E was before, it's going to be equal to the heat and the work. So when we combine all of these, Q plus W minus W really just gives us Q. So at constant pressure, what we're going to see is the heat exchanged. So whether it's gained or lost is going to be determined still. It's going to be dependent on that specific process, that specific reaction. But whatever heat is gained or lost is going to be equal to the enthalpy change as well. So delta H and Q are often going to be the same because for a lot of for the majority of the processes we look at, the pressure is going to be constant. So if we think about what we talked about before, heat going into the system kind of has the En, so it sounds like endothermic. So if we've got heat going into a system, delta H is going to be positive. And again, we're assuming constant pressure, so Q and delta H are the same. Whereas if heat's leaving the system, delta H is then going to be negative. It's going to be an exothermic process. And again, with the exothermic process, since we're part of the surroundings, we'll feel that heat being released. So it's actually going to feel warm to us. Whereas the endothermic, that heat's leaving the surroundings, which we're a part of. So that's why the endothermic reactions are going to feel cold to us. So an exothermic reaction could be something like a campfire. You're combusting, you're burning whatever those substances are going to be, and that's releasing heat. It feels warm to us. Whereas an endothermic reaction could be something like one of those ice packs where you have to kind of crush it in order to sort of activate it. That process is going to be absorbing energy. So it's going to feel cold to us because it's actually going to be taking the energy from the surroundings, taking that energy from us. And then when we look at the delta H, just like delta anything, again, is going to be final minus initial. So if we're looking at a reaction, the enthalpy of reaction, or that change in enthalpy, is going to be the enthalpy of the products minus the enthalpy of the reactants. And then since we're applying this to reactions, sometimes the enthalpy of reaction, since Q and delta H are going to be the same for the most part, we consider delta H to be the heat of reaction as well. And in the picture here, you can see we're just going to have some balloon filled with hydrogen. We're going to combust it, react it with the oxygen there, and we're going to be producing or releasing energy in that case. And that's why if you look at the energy diagram here, hydrogen and oxygen are going to be higher in energy than the water vapor that's going to be produced when they actually burn together. So since the energy is being lost by the system, it's going to be gained by the surroundings. So energy is going to be leaving the system. That's why it's going to be an exothermic process. That delta H is going to be negative. All right. And then with these chemical reactions, we can sometimes put the delta H right with it. So in this case, calcium plus water, producing calcium hydroxide and hydrogen gas, is going to have a enthalpy of reaction of negative 431.12 kilojoules per mole. So notice that with this, we have a per mole basis, because the more of a reaction we have, the more of this heat that's going to be either gained or lost, depending on the reaction itself. So in this case, negative 431.12 kilojoules means that the products are going to have that much less energy than the reactants because they're going to be losing that amount of heat. So again, this is a negative value going to be exothermic, would feel warm to us because this energy is going to be going from the system to the surroundings. And if we look at the energy diagram here, we can see just that. So calcium and water to start, higher up than the calcium hydroxide and the hydrogen gas is going to be getting produced. But with the enthalpy, kind of just like I alluded to, it's on a per mole basis because this is going to be an extensive property, meaning that it's going to be dependent on how much we actually have. So if we've got the same reaction, but we've got a lot more of that reaction occurring, the amount of heat being exchanged is going to be much greater. And then what we're also going to see is that the certain reactions are going to be reversible, meaning that we could take the reactants, convert them to the products. We can also, in some cases, take the products, convert them back to the reactants. And when we're looking at those reactions, when we're looking at the delta H in one direction, the delta H of the other direction is going to be the same number, same magnitude. It's just going to be the opposite sign. So if we look at this one, going from calcium and water to calcium hydroxide and hydrogen, going to be negative 431.12 kilojoules per mole. If we were to reverse this and take calcium hydroxide and hydrogen, convert it to calcium and water, then it would be positive 431.12. And then also with this one, we're going to see that the state of those products and reactants are going to matter. So the state of matter is going to be important, whether it's a solid, liquid, or gas, even if it's the same formula in those chemical equations. If the state of matter is going to be different, then the delta H is going to be different as well. But with the first one, thinking about it as an extensive property, with the example here, the combustion of methane, so CH4 is methane, burning it in the presence of oxygen to produce carbon dioxide and water. With these ones, like I said, it's going to be kilojoule per mole of reaction. What that means is that if we had 1 mole of methane plus 2 moles of oxygen, giving us 1 mole of carbon dioxide and 1 mole of water, that would release just over 800 kilojoules of energy, of heat. 2 moles then would be if we had 2 moles of methane, 4 moles of oxygen, producing 2 of each of these. It's going to produce twice as much energy then because we have twice as much of a reaction. And then half a mole or 0.1 of a mole of reaction would just be 0.1 or 0.5 times whatever these coefficients are going to be. So the per mole reaction can be kind of a weird concept. But with it, we're just looking at if we then take this reaction and scale it up by 2 or 0.1 by 0.5, we're going to see the delta H is going to change accordingly. So for the half mole of reaction, we get 401 rather than 802 kilojoules being released. And then 0.1, we're only going to have 10% of that reaction. So that's why we wind up with negative 80.2 rather than the 802. And like I said, with the calcium example, if we just change the reactants and the products around, the delta H is going to have the same magnitude. So in this case, if we took carbon dioxide and water and produced methane and oxygen, the heat exchange is going to be the same magnitude, 802. The only thing that's going to change is that sign, so positive or negative, depending on which direction we're actually going. And then the final piece with the states of matter again. With both of these, if you look at the formula, they're exactly the same. So methane plus oxygen, carbon dioxide, and water. The only thing that's changing here is with the top one, we've got water vapor. Bottom one, we've got liquid water. And that's why we can see the delta H for these are going to be slightly different. So 802 kilojoules for the water vapor reaction, 890 kilojoules for the liquid water one. And if we look at these ones specifically, it should make sense why we see them decrease. So in both cases, we're going to see, I'll do R for reactants, and then P for products. And this could be the first one here. Whereas the second one, then, we're going to lose a little bit more energy. So we're going to wind up going something like that. Actually, I'll just do blue for the entire thing. Because with these ones, if we think about water vapor versus liquid water, The water vapor is going to be higher temperature. It's going to be a gas. It's going to be moving around faster, so it's going to have more energy. Whereas the liquid, lower temperature, going to be moving slower, going to have less energy overall. So if we're converting it from the gas to the liquid, this process is going to release energy. And that's why we're seeing more of an energy loss occurring there. So we've got more energy released because we've got the liquid water versus the water vapor, which is going to have higher energy as a gas there. And then with the enthalpy, we'll see that that's also going to be a state function. So that's going to allow us to do a couple of things in terms of when we're actually calculating it. That's going to come into play mostly with these bottom two here, but the calorimetry is how we can actually set up experiments in the lab in order to determine what this heat exchange is going to be, what this heat of reaction is going to be. And the reason we're going to be using calorimetry is because we can't actually measure the enthalpy of these directly. So we can't know the enthalpy of methane and oxygen, can't know the enthalpy of carbon dioxide and water, but we can determine the enthalpy change between the two. And with the calorimetry experiments, we're going to actually have a lab where we do something like this. This is going to be known as a styrofoam cup calorimeter. So it's going to be a pretty low-tech sort of setup, but it does actually work fairly well. And the way we have it set up is there's going to be a styrofoam cup full of water. And then with it, we'll have just sort of a cork stopper or just something on the top to prevent heat from being exchanged as easily from the container to the outer environment. And then within there, we'll have a glass stirrer just to make sure everything's mixing well, and we'll have a thermometer. Because with this, what we're going to be able to do, if we're thinking about constant pressure, Q and delta H are going to be the same. So if we can measure the heat gained by the water, we can actually determine the heat lost, or the opposite way around even. But if we know the heat gained or lost by the water, we know the heat gained or lost by the system itself. So we can kind of indirectly measure that heat change. And again, the reason we're going to be able to do this is because with the reaction, the water, even though it's going to be right there, is actually going to be part of the surroundings. And in order to do this, we're going to need to know a couple of different things. And we've got this equation at the bottom that's sometimes known as the MCAT equation. So it's called the MCAT equation because it kind of looks like MC, A, and T. But the A is really just the delta sign, so change for temperature. M is going to be the mass, and then C is going to be the heat capacity. Essentially, how much energy does it take to increase the temperature of that substance? And with heat capacity, the heat capacity is going to be kind of related to the container itself. So it's going to be something that we kind of have to calculate individually, and we'll see in the lab exactly what that is. But what we also have is the specific heat. And what this is going to be is joules per gram per Kelvin or per degree C. So how much energy, the joule unit, is needed to raise 1 gram of whatever that substance is by 1 degree Celsius or 1 degree Kelvin. Because Kelvin and Celsius both change at the same scale, they're just offset by 273. But a 1 degree Celsius change is the same as a 1 Kelvin change. That's why it doesn't actually matter what unit we have here, because the delta T is going to be the same. But this is going to essentially tell us how fast a substance heats up or cools down. Because with water, we'll see it's got a relatively high specific heat. It takes 4.18 joules per gram to raise it by 1 Kelvin. Whereas if we look at something like iron, 0.45, so it takes about 10% as much energy. And that's why if you think about boiling water for pasta or something, you put your pot on the stove and start heating it up. The metal itself is going to heat up much quicker than the water will, just because the metal is going to have a much lower specific heat. So it's going to take much less energy to raise that the temperature of the metal by 1 degree than it will with the water itself. And then this has important environmental implications because water, large bodies of water, can actually regulate the air temperature. So living near an ocean, for instance, helps it keep the air temperature from getting too cold in the winter or too hot in the summer, just because it's going to take a lot of energy to change the temperature of that water. Whereas in the middle part of the country, where there's less water, the temperature is going to change much quicker, and that's why we can see it get very hot in the summer or extremely cold in the winter. And then with it, the specific heat capacity, like I said, so looking at the table down here, this is going to be on a per gram per degree Kelvin basis. Per gram, or again, per degree C or per Kelvin, doesn't actually matter. But it's going to be on a per gram basis, whereas the heat capacity is going to be sort of for the styrofoam cup, for instance. How much energy does it take to change the temperature by 1 degree? But they're going to be similar ideas. When we're looking at the equation here, we think about it, we're going to have mass, so we're going to have a gram unit. We're going to have change in temperature, so we're going to have Kelvin or degree C. So when we're looking at C here, we're going to have the specific heat, so that we just wind up with that energy unit for joule. So if we're looking at water, for instance, 4.184, the mass of it, if we had 100 grams of water, the grams would get canceled. And if it changed 20 degrees, the temperature change would cancel as well. So we'd just be left with the energy unit there. We would know how much heat was used to either heat up or cool down, whatever that was. Okay. So if we look at the example here, if you want to give yourself a little chance to practice with this one, you can. But we're just going to be using the MCAT equation, so MC delta T. And for this one, we're asked how much heat is needed to warm 250 grams of water from 22 degrees C, so about room temperature, to just under the boiling point at 98 degrees C. And then we're told the specific heat of water is going to be 4.184 joules per gram degree C. So when we're looking at, we've got this Q is equal to MC delta T equation. We're solving for Q. So we need to know the mass, specific heat, and change in temperature. And we have all of that information. So we can just go ahead and start plugging it in. So for the mass, we're told 250 grams. And with these calculations, the big thing is just making sure that those units match up. So if we look at quickly the units on specific heat, joules per gram degree C. So that means our answer for energy, our answer for heat is going to be in joules. And we need the mass to be in grams. And then the temperature, again, doesn't actually matter just because that's going to cancel. But if we were given kilograms here, we would just need to convert one of those so that they match up. Okay. But then we've got the C, so I'll put in parentheses times 4.184. And then again, it's going to be joules per gram. And then I'm going to do degrees C. And then for the change in temperature, just remember delta anything is final minus initial. So in this case, we're heating it to 98 degrees. We're starting, though, at 22. And then I'm leaving the 0.0 off here just because it's easier to write, but we really have 98.0 and 22.0. So we've got 3 sig figs in all of those temperatures and the masses. So we should have 3 sig figs in our final answer. So when we go through and actually plug this one in, what we're going to see is, since we have a temperature change of 76 degrees here, really, we've got 250 times 4.184 times 76. And we're going to see that's going to be equal to 79,496. And that'll be joules. So we can just round that to 79,500 joules. And then for a question like this, since it doesn't actually specify the unit, I would just keep it in joules. Just make it simple, give yourself one less chance to just mess something up. But if it did want kilojoules, we're just going to move that decimal over 3. So we would see it would just be 79.5 kilojoules. So if we were actually to take a 250-gram sample of water, heat it up from 22 to 98 degrees, it would take almost 80 kilojoules of energy in order for that temperature change to occur. All right. And then with this one, when a student mixes 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 degrees C to 27.5 degrees C. Calculate the enthalpy change of the reaction in kilojoules per mole HCl, assuming that the calorimeter loses only negligible heat. So we're going to assume any heat gained by the water is going to be heat lost by the system. In reality, there will be a small amount that's just lost to the greater surroundings. But it'll typically be a small enough value that it won't change it too drastically. And then with this one, we're going to assume that the total volume of the resulting solution, since we had 50 milliliters of each, is going to be 100 milliliters total, which is probably pretty reasonable since both of these are water. But in some cases, if you do have different solutions, the volumes aren't always additive. But since these are going to be aqueous solutions, it seems reasonable that we would have 100 milliliters as a result. And then with it, we're going to be looking at the MCAT equation initially. But if we look at the units we want to have here, calculate the enthalpy change of the reaction in kilojoules per mole. So what we're going to have to do is basically figure out how much heat was exchanged based on the amount of reaction we had, figure out how much HCl actually reacted, so we can scale it up to a per mole basis. So we're going to have to do a couple different calculations here. All right, so with this one, if we set it up, we're going to have 100 milliliters of solution, and it's going to be 1 gram per milliliter. So when we're thinking about the mass here, what we're really going to have is just going to be 100 grams. And then for the C, since we're just thinking about an aqueous solution, we're just going to have 4.184 joules per gram degree C. And then for the temperature change for this one, it's not crucial that you account for it at this step. You could do it at the very end. Just think about what the sign should be. But since the temperature of the water is increasing, what we're going to see is that the energy of the system is actually going to decrease. So what we can do is just flip around these temperatures. So 27.5 is really the final temperature of water. 21 would be the initial temperature. But since that's going to be related to the surroundings, what we can do is just switch those temperatures here and just do 21.0 minus 27.5 degrees C. And again, you could do this at the very end. So you could just go through, get the energy change, because it's going to be the same, just depending on the direction that's going to determine the sign. So you could go through, do the entire calculation, and then just think about heat's being released from the system, so delta H should be negative, or we can account for it here with just switching around those temperatures. Now we're going to have a negative delta T, which will give us a negative Q. And when you go through and actually calculate this one, what you're going to see is you're going to get 2719.6, and then this is going to be in joules. We have ultimately want our answer in kilojoules per mole, so I'm just going to then take this and just automatically, whoops, and this should actually be negative. Let me just change that quick. And again, it's negative because I switched around the temperature units, or the temperature values rather. So really just move this decimal over 3. We're going to have 2.7196 kilojoules. And right now, we've got extra sig figs, but this isn't going to be our final answer, so that's why I'm just keeping all of the values from the calculator. Otherwise, we want to round this to 3. So we'd really want negative 2.72 kilojoules. But at this point, I'm just keeping all of the values there. And then what we're going to do to get this on a kilojoule per mole HCl basis is figure out how many moles of HCl actually reacted here and just divide it. Because if you think about it, if we had 2 moles of HCl in this reaction, we could take this value here, divide it by 2, and figure out how much heat was exchanged on a molar basis. But in this case, what we're going to see, since we know the volume, we know the concentration, we can really do, we'll convert this to liters, 0.0500 liters. And then molarity is really moles per liter. So we can just multiply those two together. And what we're going to see is we'll have negative 2.7196 kilojoules of energy released for every 0.0500 moles of HCl. So we'll just wind up dividing those two. Oops, and that should be mole. That got really bad there at the bottom. Mole HCl. And then what we'll see is this is going to be equal to negative 54. And then in this case, I'm going to keep the sig figs. So we'll just have 3. So negative 54.4 kilojoules per mole HCl. And again, the actual heat exchange in this particular reaction was much less, just barely under 3 kilojoules, because we have much less of a reaction actually taking place. We've only got 5% of a mole, so that's why we've really only got a small fraction of that energy being actually exchanged in this case. But again, with this one, you could have kept the temperature the same. I like to do it initially just so I don't have to worry about the sign. I can just keep it through the entire thing. But we could have done this for the heat exchange, or the heat gained by the water would have just been a positive value divided by the moles of HCl. And then we could just put the negative there because the system is releasing the energy in this case. That's why the water, which is actually part of the surroundings, is warming up. All right, so with a couple more, if you want to practice on your own, feel free to do that, but I'm just going to start going through them. All right, so for this one, we'll be doing pretty much the exact same thing. We've just got a different reaction. And what I'm going to do is initially just figure out how many moles of the silver nitrate we have. So again, we can move this decimal over 3 to get to liters and just multiply it by the molarity. So what we're going to see is we'll have 0.00500 moles of AgNO3. And then what I'm going to do in this case is actually just do the calculation for Q with this. So I'm just going to set up the fraction where we'll have the moles on the bottom, and then we'll have Q equal to MC delta T on the top. So for this one, we're still going to have 100 grams because once again, we've got 50 milliliters plus 50, and we're thinking about the density of water, so 1 gram per milliliter. It's still got that same C value, 4.184. And for this one, I'm going to leave the units off just so I can save myself the writing. And then with the temperature change, again, I'm going to switch it around since that gives us the temperature of the water rather than the surroundings, or rather than the system. So I'm going to do negative 0.91 degrees C. And then when you go through and actually plug this one in, do the calculation, what we're going to see is we'll get negative 61,000, or negative 76,000, excuse me, 149. It's going to round it to the whole number. But this is going to be for joules. We want it in kilojoules, so again, we'll just move that decimal over 3. So we should get negative 76.1 kilojoules per mole. And then I think there's going to be one more practice one that we can look at. And again, if you want to practice on your own, feel free to kind of just pause it and do it by yourself. But in this case, suppose 23.5 grams of aluminum is heated in a boiling water bath to 100 degrees C and then put in a calorimeter containing 130 grams of water at 23 degrees Celsius, excuse me. If the final temperature of the water is 26 degrees C, what is the specific heat of the aluminum? So this one's going to be a little bit different in terms of what we actually need to do. So if you want to kind of give yourself a practice with this one, a chance to practice on your own, just pause it, and then I'm going to start working through it myself. Okay, so for this one, there's a couple things we need to think about, and what we need to think about is the heat of aluminum, gained or lost, is going to be equal to the heat gained or lost by the water. So in this case, aluminum is going to wind up losing energy, water is going to wind up gaining it. But what we need to do in order to make sure that these numbers actually match up is just make one of these negative. So we can put a negative sign in front of aluminum. And the reason I did that is just because the heat for aluminum is going to be negative just because it's going to have a negative temperature change. So if we just make the entire thing negative, that becomes positive, which we'll have on the right-hand side there. So for each of these, we can set up an MCAT equation. So Q is equal to MC delta T. Just on the left-hand side, we'll be focused on the aluminum. So the mass is going to be 23.5 grams. C is what we're going to be looking for. And then I'll do C. Oops, tried to do AL there, but it kind of got a little wonky. And then the temperature change, since we heated it up in 100 degrees of water, if you think about it, the water is not going to get above 100 degrees. If it does, it'll turn into the vapor. So if we leave the aluminum in there, the temperatures will eventually even out. So we'll have an initial temperature of 100 degrees C for the aluminum, and then it'll cool down to 26. So we'll really have 26 minus 100. That's just going to give us negative 74 degrees C. And then with it, again, we put the negative sign in front of it, just so that it actually winds up equaling the heat gained by the water. Because now if we've got a negative temperature change, a negative mass, again, really can't be negative, but we could just kind of do something like this. Put the entire thing in brackets and have the negative sign on the outside. But now on the right-hand side, we can do the same thing, but now we're focused on the water. So instead of 23.5 grams, we'll have 130 grams. C for water is still going to be that 4.184 number. And that's going to be joules per gram degrees C. And then the temperature change in this one going to be much lower because we've got a lot higher of or a lot more mass of the water, and it's got a much larger specific heat. So in this case, we're only going to see a temperature change of 3 degrees. So what we can do, multiply the entire right-hand side. So 130 times 4.184 times 3, divide by negative 74, divide by 23.5. And what we're going to see is that the specific heat of aluminum, and if we pay attention to sig figs, we had 3 in the masses, or 3 in the temperatures, 3 in the first mass, 4 in that mass. So we're going to have 3 sig figs overall. So we should see 0.938. And then this is going to be the same units as the specific heat of water. So it'll be joules per gram degrees C. And if we kind of just think about what we have on both sides, we've got a much smaller mass, much smaller specific heat on the left, but we've got a much greater temperature change. So we can at least kind of just double check to make sure if these numbers even kind of make sense, just to make sure that we did plug everything in. We divided where we should have, we multiplied where we should have, just to make sure we've got the right info there. But again, the reason this one works is because the heat gained by the system, or in this case, the heat lost by the system, if we want to think about the aluminum as the system. But the heat exchanged is going to be the same in terms of magnitude. Only thing we see is the sign's different. So the heat lost by the aluminum is equal to that heat gained by the water. And then with this one, I talked about the styrofoam cup calorimeter before, so we can have the reaction occurring in water. Any heat released by the system is going to be gained by that water, so we can essentially indirectly calculate it that way. We can do something similar with a more precise setup here. So this is what's known as a bomb calorimeter. And the way it works is very similar. So we've still kind of got that container filled with water. we've got the temperature, or the thermometer here to measure the temperature change of this water. We've got a motorized stirrer just to make sure everything's moving around evenly. So if you think about it, we're going to have this little container where the reaction is going to occur. And the reason this is going to happen is because we're going to essentially put our substance in this little container, hook it up to these wires, pump it full of oxygen, and then we can ignite it, and it's just going to burn whatever that sample is. And however much energy is released from the sample is then going to be gained by the calorimeter itself. And then based on the way that you set this up, you can use a known substance first to essentially calibrate your calorimeter. Because if you think about it, heat's going to be lost to the water. It's also going to be lost to the metal calorimeter itself. So you need to do an initial calculation to calibrate it. But once you know the heat capacity of the calorimeter, any temperature change in the water can then be used to determine how much energy was released from the burning of that substance, which then allows us to calculate the enthalpy change. But with it, since the volume here is actually not going to change, so if you think about the bomb calorimeter, we've got this metal container, the volume of it's not actually going to change. So the pressure will actually change slightly. And then with it, what we'll see is that's actually going to give us delta E. But it's going to be very, very similar to delta H. So that's why this is still going to work. May not be perfect, but it's going to be a very good measurement anyway. So if we look at a question like this one, methylhydrazine commonly used as a liquid rocket fuel. So if we take that hydromethylazine and combust it, react it with oxygen, we can see the reaction that's going to occur. So we'll produce elemental nitrogen, carbon monoxide, and then water. And this question in particular is telling us or asking us if we had 4 grams of methylhydrazine and we combust it in a bomb calorimeter, the temperature of the calorimeter increases from 25 to 39 degrees, 39.5 degrees. In a separate experiment, the heat capacity of the calorimeter was measured to be 7.794 kilojoules per gram C. What is the heat of reaction for the combustion of a mole of methylhydrazine? So with this one, the first thing I want to point out is the heat capacity now. So not the specific heat, but the heat capacity is on a kilojoule per degree C basis, because they've already done that calibration experiment. So they know how much energy it takes to raise the temperature of that entire calorimeter. So we don't need to focus on the mass, because we know the entire container, the heat capacity basically. So with this one, what we're going to see is a similar equation. See, but we won't have the mass in there, because now we've only got to cancel out the temperature piece of it. So we'll just do the heat capacity times that temperature change. And I really shouldn't use C, because it's going to be kind of confusing there. But this is going to be for the heat capacity. So now we know 7.794 kilojoules of energy are needed to change the temperature by 1 degree. We know the temperature change by 14.5 degrees. So we can just essentially multiply those two together. So if we do 14.5 for the temperature change times that heat capacity, what we're going to see is that that's going to take 113 kilojoules of energy. And for it, I'm going to make it negative, because again, the energy is being absorbed by the surroundings in this case. So it would be lost by the system. So instead of a positive 113, we're really going to have negative 113. But we want to figure out the per mole basis. So what we need to do is figure out how many moles of methylhydrazine we actually combusted. And in order to do that, we need to get the molar mass. So we're going to have 12.01 for carbon, 6 times 1.008 for the hydrogens, and then 28.02 for the nitrogens combined. So what we're going to see is this is going to have a molar mass of 46 point, I'll round it to 0.08 since we only had 2 sig figs after the decimal for carbon and nitrogen. And that's going to be grams per mole. We've got the grams here. So if we do 4.00 grams divided by that molar mass, what we're going to see is 46.08. We're going to then wind up with 0.0868 moles, which means the delta H, that came out very terrible. So the delta H of this reaction will be negative 113 divided by 0.0868. And we'll get a very, very big number. Yeah, kilojoules. And then with this one, if we wanted sig figs, because we've got 3 sig figs in the mass here, we could write this one in scientific notation. So you could do negative 1.30 times 10 to the third kilojoules. But for this one, I'm not too concerned with the sig figs, just the process. But again, we can figure out the heat exchange similar to the previous ones, but now that we've got the heat capacity, so kilojoules per gram C, we don't really need to worry about the mass of that calorimeter. So that's why we've just got the heat capacity times the temperature change, gave us the amount of heat exchange for that particular amount of reaction. And then we could take the amount of moles of that substance just to change it to the delta H on a per mole basis there. And then for this one, since it's the combustion, we could also call this the heat of combustion rather than just the heat of reaction as well. All right. And then with the delta H, like I said, this is going to be a state function where it's just going to be concerned with the initial enthalpy, the final enthalpy, and just the change between those two. But the steps themselves aren't going to be important, or the path between those two isn't going to be important. So what we're going to be able to do is use the enthalpy for different reactions and essentially combine them. We may have to sort of flip them around, multiply them by some coefficient, but we can essentially take multiple reactions and then organize them in a way that the collection of those reactions is going to add up to the reaction that we're interested in. And then the sum of all of those enthalpy changes for the other reactions will be equal to the enthalpy change of the reaction of interest. So we'll be able to kind of see that with an example or two. But if you look at the reaction here, we could be going from methane and oxygen to carbon dioxide and water. So we could be looking at the combustion reaction, and that's going to release 890 kilojoules of energy. But instead of going directly from methane and oxygen to carbon dioxide and water, if we first go through and transfer it to carbon monoxide, water, and oxygen gas, and then get to those final products, what we're going to see is the enthalpy change of those combined steps is still going to be equal to the enthalpy change of just that overall reaction. And that's going to be the basis of Hess's law. We're going to be able to add up multiple pieces in order to get the enthalpy change of a single reaction. And if we look at this one in particular, actually, we're not going to be able to really see here very well how it's actually written, but we'll see it as we go through different examples. But again, the reason this works is because delta H is going to be a state function. So it doesn't matter if we go directly from reactants to products or if we go through sort of an intermediate. As long as the initial and the final are the same, that delta H is going to be the same. So negative 890 is the same thing as negative 607 plus negative 283. Okay, and if we look at an example like this one, so we've got, this is going to be ethene plus hydrogen gives us ethane. So this would really be two carbons that are double bonded together, and then each of them has a hydrogen coming off of them. And then we're going to take hydrogen gas and then just break that double bond to a single bond so that each of the carbons now has a third hydrogen coming off of it. But if we want to figure out the enthalpy change of this reaction, we could take the enthalpy changes of different reactions and essentially use those to add up to this one. And when we do this, what we're ultimately going to be looking at is taking the collection of these reactions, and we may have to flip them around. We may have to change them by some coefficient. But when we go to add up the collection of these ones, everything that's on the left is going to add up. Everything on the right is going to add up. So we'll kind of just take everything on the right, add them up all together to give us the products. But if we've got things on opposite sides of a reaction, those are going to cancel. And I think describing it can be a little bit tricky in terms of exactly what I mean. But as we go through examples, I think it'll clear it up. Because with this one, if we look at it, we've got a couple of different reactions. But the second reaction is the only one that contains C2H4. So when we're taking these reactions that we kind of have in this little sort of table at the bottom, we're going to want to kind of piece them together so that they kind of match up with this one. So for the first one here, C2H4, we've got 1 mole of C2H4. That's exactly what we need here. So I'm not going to change anything about this reaction. With the bottom one, though, we've got C2H6 on the left-hand side. We need to get C2H6 on the right-hand side. So what I'm going to do is, and we only need 1 mole of each, so I'm not going to multiply this by any coefficient. What I'm simply going to do is switch it around. So we'll have 3H2, or 3H2O rather, plus 2CO2 goes to C2H6 plus the 7/2 of oxygen. And then with that, remember with the delta H, the reverse reaction is still going to be that same heat exchange. It's just going to be the opposite sign. So now we'll have delta H is equal to positive 1560. And then what I'm going to do, just so this gets a little bit less confusing, is just cross this one off entirely. All right. And then when we look at the first reaction, this is going to be the only one where we've got hydrogen present. So we've got water, but we don't have H2 by itself in either of these bottom two reactions. We've only got it here. And again, we've got 1 mole in our reaction of interest. We've got 1 mole in this equation we're given. So we don't need to multiply this one by any coefficient. But now what we can do is take all of these reactions and essentially just add them all up. And with things that are on the same side, those are going to add together. So if you look at it, we've really got on the right-hand side here, 3 water molecules. And actually, you can just go through and add up everything on both sides first, too. So that might be easier, at least for this first one. So on the left-hand side, we've got 3 water molecules plus C2H4 plus H2 plus 2CO2 plus, and then we've got 3.5 oxygens now. So I'll make that a fraction. 7/2 O2. And then we'll do the same thing on the right-hand side. So we've got 3 water molecules between those first 2 equations combined. So 3H2O. I've got to get a better system with actually writing this stuff out. So 3H2O plus 2CO2 And then if we go back to the bottom one now, we've got C2H6 and then 7/2 H2O. So what we can do now is look at what we have on both sides of those reactions. And kind of similar to when we were looking at the spectator ions from chapter 4, I think that was, wherever we were looking at the solutions. Anything that's on both sides and that's exactly the same, we can just cancel. So with it, we've got 3H2O. And with it, I should also mention, if the coefficients are different, they're not going to cancel evenly. So if we had, let's say, 2H2 on the left, that would cancel 2 of the H2Os on the right, but we would still be left with 1. But in this case, we've got 3 on each side, so those are going to fully cancel. Same thing with the carbon dioxide. We've got 2 of those on both sides. Those are going to cancel. Same thing, 7.5 O2. So when we look at what's left here, now we've got C2H4 plus H2 plus C2H6. So that's our reaction of interest. So what we can do then is just take these delta H values and add them up. And when we do that, we just want to consider any changes we made. So in this case, we flipped around the third reaction. So we want to account for the positive 1560 kilojoules for that one. And if we needed to multiply these by any coefficient, so let's say maybe we had a 2 in front of the hydrogen here, that means we would have needed to double this first reaction. So that means we would have to double that delta H as well. But in this case, we don't need to do that. So we can just do negative 285.8 minus 1411 plus 1560. And what we're going to see is the delta H of this reaction is going to be equal to negative 136.8. And then for this one, since those first two or those last two don't have decimals, that would really just get rounded to the whole number based on sig figs. So we'd have negative 137 kilojoules released. So with the reaction of ethene with hydrogen to produce ethane, that reaction, and then it would be really per mole if we wanted to put that in there as well. But it's going to release negative 137 kilojoules of energy. Okay. And then with the next one here, kind of the same idea. The enthalpy of a reaction for the combustion of carbon to carbon dioxide is negative 393 kilojoules per mole carbon. And the enthalpy of the combustion of carbon monoxide to carbon dioxide is negative 283 kilojoules. Use this information, determine what the heat of combustion or the enthalpy of combustion of carbon to carbon monoxide would be. And again, we want to think about how we need to adjust these equations. And this one going to be maybe a little bit easier, because with it, if we look to see where we only have one of these formula, carbon to start, we only have in this first reaction, we need it on that left-hand side, and we need just 1. So we got exactly that. So we don't need to change anything about this top reaction. But with the second one, we need carbon monoxide as a product. So we've really got to flip this around. So we really want CO2 goes to carbon monoxide plus 1/2 oxygen. And so we'll get rid of that. That'll make this positive. And actually, I'll just do a positive sign there, because we flipped that reaction around. So the enthalpy change, the sign changes as well. But now if we look at what we've actually got in those two reactions, CO2 is just going to cancel because it's on each side. And then with the oxygen, we've got 1/2 on the right of the second equation, but we've got a full oxygen on the left. So what we're going to see is that half's going to get canceled, and we'll ultimately just be left with a 1/2 there. So now we've got carbon plus 1/2 oxygen, nothing else on the left-hand side. And then the only thing we've got on the right is just going to be that carbon monoxide. It's exactly what we have in the reaction of interest. So what we're going to see is that the delta H of that reaction, that combustion of carbon to carbon monoxide, is going to be equal to the heats of those individual steps summed together. And what we're going to have there is going to be negative 110.5. And then that'll be kilojoules, just because that's the unit we had in those previous two up there. But again, with this one, it's going to be negative 110 because we flipped around the second one. So we've really got positive 283 here. But it's still negative just because that first one has a larger magnitude with the negative sign. And with these, they're all going to be pretty much the same thing. The number of equations we have may differ. How we need to manipulate them in terms of which ones we need to flip around, or if there's a coefficient we need to multiply them by, may change. But the overall idea is kind of just like a little puzzle, seeing how we can take those different equations and have them add up to the equation that we're interested in. Okay. And if we've got another one here, we can get through this a bit. All right. So if we look at one more here, in this case, we want to take NO plus an oxygen atom, form NO2. And we've got a series of equations. So again, I'd always recommend that you pause it, kind of give yourself a chance to work through it on your own. And then if you get it, you can check to see how you did. If you struggle, you can always unpause it and just kind of follow along and see the process again. But we want to take these three equations, have them add up to the example we have here. And with it, we've got NO and NO2 on the correct side there. So we don't need to change anything about that first equation. But with the bottom two, we're going to have to switch those around. And the reason we're going to have to do that is because if you look at the O3 here, we don't have that in the correct spot. And then, so really what we're going to have to do is switch this one around. So I'll do, actually, to make it easy for myself, what I'll do is basically just cross all of this out and then change it just to O3. And then by doing that, we'll change the sign of this one. So we'll really have positive 142 there. And then with the bottom one, we're going to have to do a little bit more work. So we're going to have to switch it around. But we're also going to multiply it by 1/2. Because if you look, we've only got a single oxygen atom here on the left. So we need to switch this around so we get the oxygen on the left. But we've got a 2 here. We only want a 1. So we've got to really multiply this by 1/2 and then flip it. So since we're going to do that, what I'll do is 1/2 O2. And then I'll just cross this out. And since we multiplied 1/2, I'm also going to cross out that 2. And then just say that this is times negative 0.5. So I'm multiplying it by negative 0.5 because we flipped it and also cut it in half. So what we're going to see there is 495 is really going to be 297.5. And it'll really be 297, negative 297.5. But if we look at these reactions and just add them up, what we're going to see is O3 is going to cancel O3. With the oxygen, we've got one oxygen here and another half on the right. So we've really got 1/2 on the 1 and 1/2 on the right. 3/2 on the left is the same thing. So those oxygens are going to cancel. And now we're just left with NO plus oxygen gives us NO2. So that's what we want to have for our reaction. So now we can just change or we can add up those delta H's. And for the first one, we didn't change it at all. So we can just use negative 198.9. For the second one, we flipped it around. So that's why we've got positive 142.3 there. And then for the final one, we flipped it around and multiplied it by 1/2. So that's why we've got negative 297.5 there. And what we're going to see is the overall sum of those is going to be negative 354. And then that'll be 0.1 kilojoules. So like I said, with all of these, it's essentially just going to be a little bit of a puzzle so we can see how we have to manipulate those given reactions in order to get the one that we're actually interested in. So in this case, the reaction of NO plus a single oxygen atom giving us NO2. would release 300 or negative 300, or actually it would release 354.1 kilojoules, or the delta H would be negative 354.1 kilojoules. And with these are all going to be per mole, so we could also say per mole of reaction. All right. And then the final piece here, what we're going to look at is the enthalpy of formation. And what this is going to describe is the enthalpy change that's associated with creating that compound from its pure elements. So rather than nitrogen and an oxygen atom forming NO2, the delta H of formation would be taking diatomic nitrogen and diatomic oxygen and combining those to form NO2. And with it, standard enthalpies of formation are going to be the only thing that's different with the sign there. So if we go back one, delta HF, the F stands for formation. So taking those pure elements to form whatever that compound is. When we've got the little circle there, that just means we're going to have it under the standard conditions of 25 degrees C and 1 atmosphere of pressure. If we have delta HF without that circle, it just means those were measured at some other conditions. But with this table here, what these delta H of formations are showing are what the energy change is going to be, or the heat change is going to be for taking those pure elements and forming whatever that that compound is going to be. And similar to Hess's law, what we can do is essentially look at the change and the difference there. So if we have a reaction, what we're going to be able to do is look at the heat of formation of those products, multiply by whatever the stoichiometric coefficient is in that reaction. And we'll do that for every product. And then the summation sign here, so that E-looking thing, just means we're going to add all of those up. And I should point out the N here is going to be different for each product if it has a different stoichiometric coefficient in that reaction. And then on the right side here, we have essentially the same thing, but for the products, or for the reactants, excuse me. So we'll look at all the reactants, look at the heat of formation for that specific reaction, multiply it by its coefficient, and then just add up all of the heat of formations for those reactants. And the delta H of that reaction then is just going to be the difference between those two. So if we look at the example here, this is going to be the combustion of so C3, some methprop, so that'll be propane. And when we look at it, again, it's final minus initial, so it's going to be products minus reactants. So this first line here, the negative 393.5, is going to be the heat of formation for carbon dioxide. And then we multiply it by 3 because we've got a coefficient of 3 there. And we're going to do the same thing for water, 4 moles times the heat of formation for water. And then we do the exact same thing for the product, or the reactants, excuse me. So 1 mole of propane, heat of formation of a little bit over 100, negative 100. And then with it, oxygen O2 is going to be in its pure elemental form. So the heat of formation of a pure element is just going to be 0. So we can essentially just ignore the oxygen. Because no matter what the moles is, anything times 0 is just going to be 0. So when we look at it, the negative 1180 is going to be for the carbon dioxide. The negative 1143 is going to be for the water. So we can add those up to get the products. And then we subtract the reactants, so minus, and then we've got a negative 103.85 for the propane. So we can kind of just do negative minus negative. We're really going to be adding that 103. So we can see a delta H of reaction in this case for a little bit over 2,200 kilojoules. And again, with it, it's going to be products minus reactants. So this top line here is for our products, 3 moles of carbon dioxide times its heat of formation, 4 moles of water. times the heat of formation of water, and then the same thing for the reactants. It's just one of those reactants is a pure element, so that the heat of formation is going to be 0. Then with this, we've got a few that we can practice with and look at here. So with it, we're looking at a combustion reaction again. In this case, it's going to be methane. And with it, I would never expect you to have any of these memorized. The only thing that you might not be provided with is oxygen, because it's a pure element, and then you just want to recognize that the pure elements are going to be 0 in terms of the heat of formation. But we can do something similar with this one, where we take the carbon dioxide, and in this case, we don't even have to multiply by anything because it's really just 1. So we'll have negative 393.5. We'll do blue for the products there. Plus 2, because we've got a coefficient of 2 for water, and then we'll use the heat of formation for water, negative 285.8. And I'm going to leave up the units here just because I'm terrible at writing with this mouse. I try to use the tablet and stylus, but sometimes that just crashes a bunch, so I've tried to get away from that a little bit. But this will give us the product side, and then we can do something similar with the reactants. Again, we can ignore the oxygen just because it's going to be 0. So on the product side, minus, and then we'll have a negative just about 75 for the methane there. So when we go through and actually plug this one in, what are we going to get there? So we'll have negative 393.5 plus 2 times negative 285.8. So on this side, we'll get negative 965.1 minus 74, so really plus 74.8. So we're going to wind up with a number just under negative 900, so it'll be negative 800 something, plus 74.8, so 890.3 there. And again, the reason this works is because it's just going to be a state function. So it's essentially doing Hess's law. It's just we're not really looking at all of the different reactions. This is going to be the heat of reaction or heat of combustion for this particular reaction there. And then with the next one, if you want to practice with your own, again, definitely just give yourself a little bit of a chance to do that. But it's going to be the same thing, where it's going to be products. Oops, that's not right. These are products minus reactants. So with it, just to save myself a little bit of the writing, with the ammonia, that'll be times 4, and then the oxygen times 5. So we don't really need to do anything with that. But that'll be our reactant side. And then with the, so what will that give us? So 4 times negative 46 is going to be negative 184.4, I believe. So on the reactant side, what we're going to see is negative 184.4. Because again, we can ignore the oxygen because it's a pure element. But 4 times the heat of formation for ammonia because we have that coefficient there. And then with the NO, we'll also multiply by 4. With the water, we'll multiply by 6. And with the NO, we just want to recognize that that's going to be a positive number in this case. So we want to account for that, just make sure that we have the signs correct. So with our product side, what we're going to see is 241.8 times 6 is we'll get a negative 1,089.6. And then when we account for the reactant side, when we subtract that negative 184, and actually what we want to make sure to do is subtract a negative. So we're really going to be adding that 184. And what we're going to see is that the delta H overall is going to be negative 905.2 there. And then with it, since we've got kilojoules, that'll just be the kilojoules. So with it, I just didn't show up the actual calculations, but the blue is just going to be our reactants. So negative 46.1 times 4 is where we get negative 184 from. And then 90.3 times 4, and again, that's positive here, times or plus the 6 times negative 241.8 gives us almost negative 1100. And then when we combine those two, when we subtract them, we get the negative 905.2 there. Oops. Okay, so we've got a few more, and this one's actually going to go back and look at Hess's law. So it gives us the delta H of reaction for a couple different reactions, and then we need to piece those together to get to the bottom one. And looking at it in this case might not be as obvious as some of the previous ones. But again, we want to try to find formulas that we've only got in one spot, because that's going to be the easiest way to kind of figure out what we need to do here. And with the bottom one, if you look, we've got NO2 on the left of the reaction of interest. We've only got N2O in that one spot. So what we're going to do is take this entire reaction, multiply it by 1/2. That'll give us 1, 1, and then 1/2 of oxygen on the right, which means we'll really have 1/2 of this. So we'll have negative 81.6 kilojoules. And then with the other reactions, again, we've only got NO2 in one spot. In this case, though, we're going to have to flip this around. So what I'm going to do, just to save myself some of the writing, and then when we flip it around, we're also going to be multiplying. Actually, I'll just do it. That'd be kind of hard to see. What we're going to be doing is taking this reaction and flipping it around, but we're also going to have to multiply it by 1/2 because we've got a coefficient of 2 here. So I'm going to do it up top here, and what we'll have is NO2 going to NO, and then 1/2 of oxygen. And the delta H of this one, so we flipped it around and multiplied by 1/2. So we're going to have positive, but we're going to have half of this number. So what we're going to see is we'll have positive 56.6 kilojoules. So I'm just going to round it up. So I just rounded it up rather than 56.55, but it's not really important. But now I'm just going to cross this one off just because we've got the actual reaction after we adjusted it at the top. And then with the final one here, there's going to be nothing we have to adjust about this one. Because if we look at it, we have NO on the right, one of them in the adjusted reaction, 2 of them in the initial one up here. So we're going to have the 3 NOs we need. And this will also allow us to cancel out the oxygens. So if we look, these 2 NOs, so NO, NO, is going to give us 3 NOs. But this oxygen on the left is going to cancel out those 2 1/2 of oxygen. And then the same thing, the N2 here is going to get canceled out there. So with these ones, you can always just take all of the reactants on the left, add them up, all the products on the right, add them up, and then just cross stuff out from that combined equation. I just don't feel like writing everything out. But we can see nitrogen, N2 is going to cancel, O2 is going to cancel. So now we're just left with 1 N2O plus 1 NO2 giving us those 3 NOs there. So now we can take these delta H values we have, and for the reaction I wrote at the top again, that's going to be a positive number because we flipped that reaction and cut it in half, so 56.6. The next one, we didn't change anything about that one, so we can just keep 180.7 as it is, positive. And then with the bottom one, we didn't flip it around, we just cut it in half. So that's why we're going to have negative 81.6. And we're going to see that's going to give us a delta H of 155.7 kilojoules. And this will be a positive number because those first 2 ones are both positive. And then we'll look at one more here before we wrap up the chapter. So again, we want to use Hess's law. And we've got a reaction at the bottom where C2H4 plus 6 moles of diatomic fluorine are going to give us 2 moles of carbon tetrafluoride and 4 moles of hydrofluoric acid. And with it again, I always try to figure out what equations we have, what substances do we only have in one spot. And for the first one here, what I'm going to do is just multiply everything by 2. Because with the HF, we've only got that in one spot, but we've only got 2 of them here. We need 4 in our final equation. So I'm just going to multiply everything by 2. So 2H2 plus 2F2 is really going to give us 4HF. And that means we'll have, what will that be? Negative 1,074 kilojoules. And then with the second one, we're going to have to do the same thing. So we've got CF4, but we need 2 of them, but we've got it on the correct spot. So we can double carbon, we can double F2, and that'll double the carbon tetrafluoride, which means we'll have negative 1360 kilojoules. So again, since we didn't change the direction of this reaction, we don't have to change the sign. We can just double the magnitude of it. And then with the final one, what we're going to have to do in this case, since we've got the ethane, or ethene rather, on the right-hand side of the reaction we're given, but we have it on the left of the one we're interested in, we're just going to have to flip this around. But we won't have to change the coefficients at all. So we'll just flip it around. C2H4 goes to 2 carbon plus 2 moles of diatomic hydrogen, which means this is just going to get flipped to negative 52.3. And again, it's just because we changed the sign, but didn't multiply the coefficients by anything. And now with it, this is going to give us our reaction of interest, because we've got, if we go through piece by piece, C2H4, we've only gotten that one spot on the bottom equation. F2, we've gotten both of these first 2 reactions, but they're both on the left. So we'll have 2 plus 4 giving us 6. 2CF4, only one spot. 4HF, only one spot. So we've got all of the pieces we need. And then if we look at the 2 carbon, those are going to cancel. Same thing with the 2 hydrogen. Those are going to cancel. So, and I guess I could cross this one out since we flipped it around anyway. But now we're just left with the stuff that we're interested in. So we can just go through and add up those different delta H's. And we'll see negative 1,074 minus 1,360 minus 52.3. And what we'll see is we'll have a negative 2,486. All right, and then that should be the end of this. Whoops.